So we're going to start our new unit on logarithms and logarithmic functions. Basically, a logarithmic function is the inverse of an exponential function. So we are going to review exponential functions a little bit so we can get into logarithmic functions. So logarithmic functions are the inverse of exponential functions. And just to review what inverse functions are, it's when the x and y variables switch, the domain and range are switched, and there's a reflected, graphically, there's a reflection in the line y equals x. So the x values become your y values and the y values become your x values. So an example of that would be f of x is equal to x squared. The inverse function of that would be the square root of x. So let's look at some general characteristics of exponential functions. The parent function for exponential functions is f of x is equal to b to the power of x, where b is a positive constant. And let's look at the graph of this. If you remember, if b is a higher integer, it's going to be more steep, and if it's lower, it's just going to be more flattened out. We know there's a horizontal asymptote at y equals 0, and you have a y-intercept at 0, 1. This will always be the case for any integer, any value of b, because b to the power of 0 will always be 1. We know the range is going to be, the domain is going to be xer, and your range is yer such that y is greater than 0 since we have an asymptote at y equals 0. So graphing the logarithmic function requires us to graph an exponential function and then take the inverse of that. So here we have the line y equals x, that's the dotted line here. And now we also have a point on the graph at 0, 1. And you know that an inverse function will just flip the x and y. So 0, 1 will become 1, 0, which is right here. And your asymptote will now be the y-axis because the exponential function has an asymptote on the x-axis, and your function will look like, your inverse function will look like this, which is essentially a reflection about the y equals x axis. So as the inverse of this function, we know that the x and y coordinates flip, and so in the equation they flip as well. So this is x is equal to b to the power of y, which is equivalent to y is equal to the log base b of x. So just to summarize our findings so far, logarithms are the inverse of exponentials. So if y is equal to b to the power of x, then the inverse of that will be, you're just switching the x and y, x is equal to b to the power of y. And then x is equal to b to the power of y can be rewritten as y is equal to log x with base b. Log x base b means the exponent that must be applied to base b to get the value of x. So as an example, log 8 base 2 is equal to, so what do we need to apply to 2 to get 8? Like what exponent do we need to apply? And the answer is 3. So domain, looking at the graph that we graphed above, the domain of a logarithmic function is that x has to be greater than 0, and the range is that everything, so yer, and your y-axis is a vertical asymptote, and we also know that the x-intercept is at 1, 0. So just as practice, it's useful for us to understand the relationship between logarithmic functions and exponential functions. So here we want to convert the logarithmic functions into exponential form. So for the first one, we know our base is 7, and and our exponent is going to be y. That's usually what we're looking for. The answer is the exponent, and that is equal to x. Okay, for b, you know our base is 2, your exponent is y, and it's equal to x. Now let's evaluate these logarithms. So here, let's convert to exponential form. So your base is 3, your exponent is y, let's say, and your answer is 9. So y here is equal to 2. Next one, your base is 2, your exponent is what we're looking for, y, and that's equal to root 2. And so, 2 to the power of y is equal to 2. We can express the square root as exponent of half, so therefore y is equal to half. Okay, for c, your base is 12. What we're looking for is y, your exponent, and that's equal to 144. And so you can say, you don't really need this step always, but it helps. Therefore, y is equal to 2. Your base is 4. Your exponent is what we're looking for, and your answer is 1/4. And so if you want to rewrite this, you might see it right away, but just in case, 1/4 is 4 to the negative 1, it's 1/4. And so therefore y is equal to -1. At this point, we're very familiar with this transformation equation. So just to recap, A represents our vertical stretch or compression. It also, if it's negative, represents a reflection in the x-axis. Your K value represents a horizontal stretch or compression or a reflection in the y-axis. Your D value is a horizontal translation, and C is a vertical translation. The general logarithmic function, or parent function, is when the base of the logarithmic function is 10. So we can write log x, when we write log x, it's actually log x to the base 10. So we don't even write it, it's just assumed. If it's not there, it's base 10. And so f of x is equal to log 10 x, so log x. The transform function would look like this, and your d value represents the change in the position of the vertical asymptote. So now let's look at what our base or parent function actually looks like graphically. So here we've graphed your blue function is your exponential function, it's 10 to the power of x, and your red function is your logarithmic function, so it's just log x, obviously to the power of the base is 10 as well. I'm just going to label our intercepts here. This will still be 0, 1, and this will be 1, 0. So that's true for any base. And we also have a vertical asymptote here at x equals 0, and for your exponential function you have a horizontal asymptote at y equals 0. So this looks very similar to the graph we saw above. The only difference is since it is base 10, it just rises a lot steeper than what I had drawn. And same with the exponential, as you can see, it's mirroring, it's reflected around the y equals x axis. Okay, so as an example, we're going to use transformations to sketch the following function and state the domain and range. So our transformed function is y equals -2 log x minus 4. And I want to use a mapping formula to get our image points. So our mapping formula is going to be xy becomes There's no k value, so it's just going to be x plus 4, that's our d value. And for our y's, negative 2, y. And there's no vertical shift, really. So now let's just get our table of values for our parent function. So here is our table of values for your log x, and that's your parent function. So if you notice, when x is 0.001, which is just 1 over 10 to the power of 3, your y value is negative 3. This is just 1 over 10 to the power of 2, which is just 10 to the negative 2. So that's our exponent. Here, same, it's 1 over 10 to the power of 1. This is just to the power of 0, because anything to the power of 0 is 1. And then 10 to the power of 1, 10 to the power of 2 is 100. So now let's use our mapping formula with these image points, and we get, this is our new table of values. So these are the image points for a transformed function. And now to graph it, so this is our parent function, and our transformed function looks like this. And notice that our d value is 4. So our vertical asymptote has shifted over 4 units as well. As another example, the logarithmic function y is equal to log of x has undergone the following transformations. So it's been vertically compressed by a factor of 2/3, horizontally stretched by a factor of 4, reflected in the y-axis. There's a vertical asymptote at x is equal to negative 2, and it's vertically translated 3 units down. So we want to find the equation of the transformed function, and we want to state its domain and range. So we are just going to work backwards here. Your a value is equal to 2/3. Your horizontal stretch, so that's k, is equal to, and it's also being reflected in the y-axis, so that's affecting your k, and that's going to make it negative 1/4. Your d value, well, that's that's affected by your vertical asymptote, so it's going to be negative 2, and it's being vertically translated 3 units down, so that's affecting your c value, so c is equal to negative 3. So now putting this all together, we have y is equal to 2/3 log negative 1/4 x plus 2 minus 3, and that's your transformed equation. So now let's figure out what our domain and range is. So we're going to just imagine what this function looks like. Your domain, the only thing that's affecting your domain is going to be your vertical asymptote. So it's going to be x is less than negative 2, and your range is going to be everything, just like all logarithmic functions. And that's it.